Up until now, we've always talked about where a function actually is. So for something like this, maybe we would be asked, what is f of 3? And so we would look at the graph and see, okay, so when x is 3, the y value that we have for this function is at 2. So we know that f of 3 is 2. For a limit, it is less about where the function actually is and more about what the function approaches. So our notation here, we're going to say the limit as x approaches 3 of f of x. And so instead of talking about where f of x actually is, we're talking about as the function gets closer and closer to 3 from either side, this function gets closer and closer to a y value of 1. So even though there's not a y value of 1 there, the limit as x approaches 3 from either side is 1. We can analyze a limit numerically by plugging in values that get closer and closer to our x value both from the left and from the right. So if we're looking at a limit as x approaches 2 of this function, first we want to note that since x minus 2 is the denominator, that we are undefined at 2. But we can see as we plug in some numbers to the left, so 1.9 and then one that's closer to 2 from the left, 1.99, 1.999, we can see that our numbers are getting closer to a specific value. They're even rounded to be the same value here. If we plug in numbers on the right, and by plug I'm saying I'm plugging in 2.1 into the function, 2.01 into the function, 2.001 into the function, and we can see that they also start getting closer and closer to that same number that was on the left. So this is what tells me that first of all this limit exists, that it's about negative 0.063, and we'll see later how we could find this algebraically and find a fraction value instead of having this rounded value. And this also tells us that at 2, there's not an asymptote, there has to be a hole, because if there was an asymptote at 2, then these values would be getting either really large positive numbers or very large negative numbers as we got closer and closer to 2, but they didn't do that. They got closer and closer to a value, so that means that there's a hole there. So we've really got 3 different types of limits. We have this limit as x approaches a, and then it'll have like a little plus sign in the superscript, which means the limit as x approaches a from the right of f of x. So this would be what f of x approaches from the right. Whereas if you have a negative in that superscript, this is the limit as x approaches a from the left. So this would be looking for what f of x approaches from the left. For an overall limit to exist, both of these values have to be the same thing. So essentially, your limit as x approaches a from the left of f of x has to be the same as whatever the limit as x approaches a from the right of f of x is. So for example, the limit as x approaches 4 of f of x, we would say does not exist. And that is because the limit as x approaches 4 from the left, so as we get closer and closer to 4 from the left, our value approaches 1. But the limit as x approaches 4 from the right of f of x, so as we get closer and closer to 4 from the right, we get closer and closer to a value of 2. So this would be our reasoning, that because the limit from the left of 4 is 1 and the limit from the right of 4 is 2, our limit does not exist. We have 3 different reasons that a limit could not exist. So remember, it has to approach the same value from the right and from the left. So our first example is just what we were looking at just now. So if there is a jump, or we've got some sort of piecewise function that is not connecting, this would be one reason, not the same from the left and the right. Our second reason would be if there's an asymptote. So if there is an asymptote, then we could have something like this where it's approaching a negative infinity from one side, a positive infinity from the other side. If they are the case that it is approaching a negative infinity from both sides or a positive infinity from both sides, we can either say that it doesn't exist because it's not approaching a value, or we can say positive or negative infinity. The last reason that a limit could not exist is less common, but still a reason that it could not exist. And that's that a function oscillates as it gets closer and closer to a value. So this is kind of fun looking, but we might have some sort of curve, and then as it gets closer and closer to C, it just kind of goes crazy. This is actually where they get barcodes from. So when you zoom in, we've got all these little bars. So because it oscillates right there, we're not able to find the limit from the left and the right. So the limit does not exist there. The last reason that a limit could not exist is less common, but still a reason that it could not exist. And that's that a function oscillates as it gets closer and closer to a value. So this is kind of fun looking, but we might have some sort of curve, and then as it gets closer and closer to C, it just kind of goes crazy. This is actually where they get barcodes from. So when you zoom in, we've got all these little bars. So because it oscillates right there, we're not able to find the limit from the left and the right. So the limit does not exist there. If you're curious, you want to see a function that oscillates, one that you can graph in your calculator is sine of 1 over x, and see what that looks like. It is interesting. So for this lesson, our main focus is just going to be to work on evaluating limits given a graph. And then for our next lesson, we'll look at some algebraic examples. Just the notation in general takes some practice. So for this first example, we've got the limit as x approaches -6 from the left of f of x. So first we're finding -6. So 1, 2, 3, 4, 5, 6. So right here. And then we're looking for the y value that f of x approaches as we approach -6 from the left. So I want to go to the left of that, and as I get closer and closer to -6, we're approaching a y value of -1. Okay, so example number 2, still looking at -6, but now we're looking at the limit as x approaches -6 from the right. So as I get closer and closer to -6 from the right, it looks like I'm approaching a value of 4. And then our step 3 here is going to look at the overall limit. So remember, if my limit from the left is -1 and the limit from the right is 4, that means that my limit as x approaches -6 does not exist. It has to be the same from the left and from the right. Skipping over to example 8, the limit as x approaches -1. This is not from the left or the right, so we're talking about both here. So as x approaches -1, from the left it approaches 2, and from the right it approaches 2. So our limit as x approaches -1 is 2. For 9, the limit as x approaches 1. So now we're on this side. And definitely, especially when it's continuous, we know that we can count on it because it is approaching the same thing from the left and right, and it is approaching -1. And then 10, our limit as x approaches 3 from the left. So we're looking at this value from the left, and we can see that as it approaches 3, it's going off to -infinity. So for a right or left-handed limit, sometimes we are more specific, but we can either say does not exist, or we can say -infinity. Either of those is fine. I do want you to go ahead and try some of these on your own, so go ahead and pause the video and try these last 8. So starting with our limit as x approaches -3 from the right, we're just looking at as our function gets closer and closer to -3 from the right, our y value gets closer to -3 as well. From the left of -3, we're also approaching a y value of -3. As x approaches -1 from the left, we're approaching a +2. As we approach -1 from the right, we're approaching a +2. For number 11 over here, as we approach 3 from the right, we're approaching either a positive infinity or we can say does not exist, but definitely the limit as x approaches 3, since we went to negative infinity from the left and positive infinity from the right, the overall limit does not exist. For number 13, as x approaches 8 from the right, we're going off to negative infinity or it doesn't exist. And the same thing for the overall limit. Since it is approaching, they're both approaching a negative infinity, we can either say negative infinity or it does not exist. The big deal to remember with limits is that it's all about what that value is approaching and not what it actually is. It's very tempting when you're used to function notation to say that the limit as x approaches -1 is +3 because we're used to finding that function, but we're looking at what is that y value approaching. So that's the end of our lesson for today, but you have completed your very first lesson over calculus. And that's why I really enjoy limits, because they're a fairly simple concept, but all of calculus is based off of them, which is pretty cool. So enjoy the rest of your day, work on the practice, and wash your hands.